Okay, we are into our last week of physics. Next week we have to start preparing for finals and actually taking finals next week. And so this week we'll probably be preparing for that. What I wanted to end with is something that we don't work with much in introductory physics, and that is the theory of relativity. What we have done throughout the entire course is called Newtonian physics. And Newtonian physics explains almost everything that we would have to deal with. But there was a problem with Newtonian physics, and Einstein identified it. And in the process of doing that, took and expanded the universe to include Einsteinian or relativistic physics. Let me give you an example of this, those of you who've taken enough math to know this. If I have a right triangle, the formula for that right triangle is a squared plus b squared equals c squared. If the entire world was right triangles, this is the only formula we would need. But it turns out that there are triangles that look like this, and there are triangles that look like this. And those of you who've taken enough math will know that these two triangles can be described by this equation. It's called the law of cosines. A squared plus b squared minus 2ab cosine of c. In fact, we did that earlier in the year. Now notice what happens. This is a special case of the broader formula. The broader formula has an extra term. It just so happens when we put cosine of 90 is 0, and that's what we have. What I'm trying to tell you is that in a very real sense, what we have done in the entire year is we've been working in a special case universe. And what makes it a special case universe is that everything that we're working with is moving at relatively slow speeds. Now that may seem kind of odd. What difference does it make what speed you're going? But it turns out that it does. So let me start, and we'll just have to see how fast I can do this. But I want to start with an idea that is not obvious. There was a time where people would have disagreed with this, but we would say that all motion is relative. What that means is your motion that you experience depends upon a particular frame of reference. So let me give an example. If you are on a boat and another boat goes by you, to you it looks like that other boat is the one that's traveling, but actually it could be that your boat is moving. Now we're pretty adept at picking up if there is a sensation of motion. And so as a result, we would know that we're moving, but if I had something where there was no ability to sense whether you were moving or not, it would be impossible for you to know if you were moving or the other person was moving. I have a story that I usually tell, and I'll have to make it real quick, but I was just learning how to drive, and I was driving with my sister. I had my learner's permit, and she was 2 years older, and in those days, if you had a driver's license, you could drive with somebody with a learner's permit. So we were driving to church, and I'm in my dad's big green station wagon, and we pull up to the stoplight to turn into. We had to make a left turn to go into the parking lot. Into the church, and I'm at a stoplight, and all of a sudden, my car starts drifting backwards, and I'm just learning how to drive. I don't want to have an accident, but my car is drifting backwards. So I slam my foot on the brake, and the car continues to drift backwards. So I throw the car into park, and I continue to slip backwards or drift backwards. And then I push the emergency brake down, and my sister is looking at me like, "What are you doing?" Well, I look over, and what had happened was the car beside me was inching forward. And because of that, it looked to me like I was going backwards. And he was doing it on purpose. When I looked over at him, he was laughing. My motion, to me, I thought that if that car next to me should have been stopped and he wasn't, I thought I was the one that was moving. That's the idea that all motion is relative. Now, there was a famous experiment. We've talked about it in the past. It's called the Michelson-Morley experiment. And it was to determine whether or not there was ether. And you may remember that they discovered that there was no ether in the universe. But what I didn't tell you at the time is that there is another really important outcome of the Michelson-Morley experiment. And that was they were shooting beams of light parallel and perpendicular to each other in the basement of the University of Chicago. And even if there had not been ether, there should have been some effect on the light from the fact that we know that the Earth is spinning. And they were trying to look for both of those. To make a long story short, what they found out is, from the Michelson-Morley experiment, the two conclusions were no ether, but also that the motion of a light source has no effect on a light beam. Now, you might say, okay, so what? So let me give you an example. Let's say that we have two kids that are playing catch. And this person throws a ball here at, and let's just say 60 miles per hour. That's a pretty good pitch. And this kid throws a ball back at 50 miles per hour. And they are standing, and I'm standing here watching them. To this person, the ball is leaving at 60, and to this person, the ball is coming at 60. To this person, the ball is leaving at 50, and this one's coming at 50. That's pretty obvious. And to this observer, he sees the same thing. That's because they're all in the same frame of reference. But now put these people, let's say, on a train car with a big window in it. You just have to pretend. And this car is moving at, let's say, 40 miles per hour. What am I going to see? What does these two, because they're in the same frame of reference, they see exactly the same thing. He sees the ball coming at 60, back at 50, but what does this observer see? He's on the ground, he's on the train platform. He doesn't see this ball going at 60, he sees that ball going at 60 plus 40. That ball is going to him at 100 miles per hour. In other words, if he just focuses on the ball goes by at 100 miles per hour. This ball, to him, would look like it's going at negative 50 plus 40. It would be going at negative 10. That ball would actually move past him at 10 miles per hour. So this ball shoots by at 100. This ball is going back at 10 miles per hour to this person. Why? Because he's in a different frame of reference. The motion of the light source has no affection on the light beam. Well, the motion of the balls here in this matter to an observer. And what Michelson-Morley discovered is that that was not true for light. Now let me explain that. Let's say that we had the same situation, but we had a person here who could shine a flashlight. And by the way, we're going to use the word c. C is 3 times 10 to the 8 meters per second. That's the speed of light. It comes from the Latin word for speed. 3 times 10 to the 8 meters per second. And he takes and he shines a flashlight at this guy. And this guy over here shines a flashlight at the other one. Right? And they're both here. And this person is standing here. Same thing.